Okay, so think of, well, trajectory is when something is moving, it traces a path X, Y, Z, and you want to sort of tune the path to serve your needs. So for example, if you are flying a plane, and if you can tune the propellers, the thrusters for rocket thrusters, the propellers for a plane, you can actually, and if you know it's the wind direction, then you can actually find a path which minimizes the energy or something like that, right? So that's what trajectory optimization is about. We'll solve this problem. The problem is that you have a car. It starts at some point. Let's fix that point to be the origin. It drives along a road, so it's a one-dimensional problem. And then it has to come to a complete stop after it has traveled a distance of d. Okay, so the conditions for the car are going to be at, let's say the time, I start the stopwatch at time t equals 0. So the position is 0. Starts with a velocity of 0. It should travel in some time uppercase t to a distance d, and should also come to a complete stop when it travels that distance. Okay, so the model of the car is simply what they call a double integrator. So a double integrator would have x double dot, which is the acceleration is u constant. So there's no drag, no resistance whatsoever. Okay, so u is the control, and it's something we need to figure out. Okay, when you are driving a car, you have access to a gas pedal and you have access to a brake. So if you put u equal to a positive value, you will accelerate the car. And if you put u equals a negative value, you will decelerate the car. And let's say that we have something like this. You have a bound of -5 to 5. So full throttle, that is, if you you drive the, you press the accelerator, depress it fully, then you get an acceleration of 5. Or not acceleration, but control of 5, whatever units it means. And then -5, if you just step on the brake pedal completely. Okay, so the constraint shows up right there. So that's a constraint, the control constraint. There's also constraints on the distance moved and the velocity. Okay, now this problem, I would say, well, and I should also say the objective. What's the objective? Our goal is to minimize the time. So we want to go as fast as possible from x equals 0 to x equals d. Okay, so in this problem, I think you can relate to it. If you're a traffic stop sign, and if you want to go to the next stop sign in the fastest possible time, what do you do? That's what it is. So what would you do in your car if you wanted to, if you were competing in a race? How would you drive the car? Full, but then if you keep full, then you just brake full. Yeah. So the strategy is to press the accelerator, the full throttle for some time, and then full brake for the remaining time, and then you'll come to a complete stop at the next stop sign. So we know the solution. We have to figure out if the optimization can produce that solution. Okay, so how do we do that? It's always nice to start with problems whose solution we know, so that way we can check our intuition. Now the solution will also be symmetric. That is, there'll be some time where you'll fully accelerate and fully brake. There's no coasting involved. Yeah, there's no coasting. That's what I think. Yeah, there's no coasting. If the profiles were not symmetric, that is, if you had more in the gas pedal, it could, let's say, constraint of +10 but -5, then you'll see that the profile will shift. Okay, so let's see if that's what we get. Now, to make this problem tractable with numerical optimization, what you need to do is you need to convert this to a what they call a parameter optimization problem. But before we do that, it's always a good idea to take this problem and write it down as a optimization problem. So if you go back to optimization, you'll see that we always, not for this one, but let's see the constraint optimization. We wrote down cost, we wrote down all constraints like so. So we need to write that down, because unless we have that form, we cannot proceed and try to solve it using a computer, right? We need this form. So let's do that first. So here's always the first step is to formulate. Think of this like the free body diagram of the dynamics world. You always have to write the formulation before you put your pen to paper and write down how to solve it. So here's the formulation. So we minimize the time. You could either write it 0 to uppercase T, which is basically saying that you minimize time. So if you're minimizing time, you better keep that as an optimization variable. Okay, you can choose how much time you're going to keep solve the problem. You also have full control over the throttle, so or brake, so that's U. Next, we need to put constraints. So we always say subject to, we have, so we'll divide x double dot equals 0 equals to u as two first order equations, because that's how we can integrate them. X1 dot is x2, x2 dot is u. So this is just breaking down one second order equation into two first order equation. X1 is x, x2 is the velocity. So we can write x1 dot equals x2, x2 dot equals u. We have bounds on u, -5 and 5. We also have constraints on the position at time t equals 0 is 0. At time t equals uppercase T, it's d. The velocity at the start time is 0. Velocity at the end time, so remember that's just x2, is 0. Yeah, are we missing anything? I think we're good on the constraints. Okay, if you want, we can identify these constraints. What else? So these are all well, these are all constraints. They're actually equality constraints. We also have equality constraints here. Okay. I will not say they are linear or not linear, because that depends on how I try to do the parameter optimization problem, which will come later. And these are the bounds on the controls. Okay, and the time t, well, I should also put a constraint on that. So the time t can be anywhere between 0 to infinity. That's also a bound. There's no negative time. Okay, now that we have formulated the problem, now we need to convert that into in a way that the minimize function can understand it. Now, we deal with, we are in a digital world, that is, our computers are digital systems, which can only understand, we can only understand discrete values. It can understand continuous values. So u is actually continuous, right? What you do between time 0 and 1 second is going to have infinite values, because there are infinite number of points between 0 and 1, right? But you cannot solve something with infinite values, because our computer can only understand discrete values. So what we do is, the first step is to discretize the whole problem. So we discretize u we assume that we're going to divide, let's say, the time interval in 10 time steps. Each time step, we're going to keep the control constant. That's kind of discretization. So instead of dealing with the infinite number of u over the time, we deal with finite number of u. So that is what is known as a what we do is a parameter optimization problem. So we'll write this as a parameter optimization problem. Especially because of these conditions. The good thing about and this one, the good thing about this, the four conditions here is that they're already discrete, in the sense you only care about x1 at one time instant and x2 at another time instant, so on. But the ones which are highlighted in yellow, those are continuous, and we need to discretize them. Okay, I'm going to show you two methods to do this. Okay, and for the homework problem which you'll be doing, you can choose whichever you want, and they have their own pros and cons. So we'll look at two methods of solving the problem. Number one is called the collocation method. The second one is known as the shooting method. Yeah, and I'll show you code, and of course we'll compare the solution from both these methods.